Okay, so for the beginning, I will recall what we have done in the previous lecture. So I will make a small summary, a short summary of the previous things that we have learned from the representation theory of Sn. So here is a kind of summary of what I explained about the Okounkov-Verschick theory. So what you see here is what we have learned is that Sn has irreducible representations, and the irreducible representation of Sn are parameterized by the partitions of n. Okay, so here I have put the partitions. So here you have the partitions of 1, there is only 1, the partitions of 2, 3, etc. And according to my convention of using the Russian way of drawing Young diagrams. Okay. Now the point in this diagram is that we represent the branching law, that is the way that representations behave when you do the restriction. When you take an irreducible representation of Sn and reduce it to Sn minus 1, we see that it decomposes into irreducible, and for each irreducible occurring of Sn minus 1 occurring in a representation of Sn, I draw a line. And we know all the multiplicities are equal to 1. So for example, this representation is decomposed into the sum of two representations of S4 corresponding to these diagrams. And they are exactly the diagrams that I obtained by erasing one of the boxes that I can erase to keep a Young diagram. So one of the corners of the diagram. Okay, so this is a branching graph. And what we know is that, well, we can, so when we do this branching, of course, we can go down, say, to S1, which gives you the last box, okay? And in the end, I get an irreducible representation of S1, which is just a one-dimensional subspace. So what this means is that every path going down in this graph from one of the partitions here, say this partition to this here, every path corresponds to a one-dimensional subspace of the irreducible representation, and this one-dimensional subspace, they form a basis of the representation. So the dimension of the representation is equal to the number of these paths. And furthermore, we can index this path by the sequence of eigenvalues of the Murphy element, so J1, J2, Jn. So they form a sequence, they have a sequence of eigenvalues. And these eigenvalues are just, you look at the path, and for each path you pick up the label. The label here between two partitions is just the content of the box that you have added to the partition. So here, for example, I have added this box here. And the content of this box, it's if you want, it's a horizontal coordinate in the middle of the box, it's -2. Okay, so here you get a -1 here, you get a +1 here, and so on. Okay, so we can index by either this sequence of numbers, which was the way that we described the theory by using the tools of Justice Murphy element, so according to Okounkov and Verschick. And okay, so we have a basis. We can compute the dimension of the representation, and even we can compute explicit matrices for generators of the symmetry group. There are very explicit matrices in this basis, for example, of the Coxeter elements, of the Coxeter generator, sorry, that is the SI. Okay. So this was the way I described the representation theory of Sn. And then we used so what we did last time was to introduce the transition measure. So what was the transition measure? Transition measure is a measure which is supported by the corners of some partition. Okay, So the corners are here. And so, sorry, it was the co-transition measure, sorry. Not yet the transition measure that we will see later, but the co-transition measure. And it is supported by so the contents of the boxes that you can erase from the partition to get a smaller partition. And then the mass of a certain point, a certain corner, is equal to the dimension of the representation that you obtain by erasing the corner from the partition, divided by the total dimension. Of course, since we have multiplicity 1, the sum of all these dimensions is equal to this dimension, so this is really a probability measure. Okay, and I have described also there is an explicit formula for this probability measure, which uses the x and the y, which are the local minima of the curves that is above, which are the contents of the boxes that you can add this time to get a new partition. Okay, so you have either the boxes that you can erase, which are the corners, or the boxes that you can add to get a new partition, and which are indexed by these numbers, y, and the formula was that this is equal to 1 over n. N is the size of the partition, so the number of boxes. The product of the xi minus yj, product over j, divided by the product over k. Okay, so this was the formula. So what we did last time was to investigate the possible limits of points, of characters, irreducible characters, normalized irreducible characters, that is. So if sigma is a permutation of S infinity, so if lambda is large enough, then this permutation belongs to Sn, so I can evaluate this quantity. And what I said is that what we did was to embed lambda into the Thoma simplex, so the partition into the Thoma simplex. So it was done using the Frobenius coordinates. So the Frobenius coordinates were just the length of these diagonals here. So the Frobenius coordinates so we have a sequence of numbers, positive numbers, P1, Pk, which give these lengths, and Q1, Qk, which give these lengths. Okay, and we embedded this into the Thoma simplex, which is just the set of all sequences, double sequences, I should say, of positive or non-negative real numbers. And we have a third number, and we have the conditions that the sum of alpha I plus the sum of beta I plus gamma is equal to 1. Okay, so all these numbers are between 0 and 1, and we have these conditions. And so we had these embeddings that just by sending this to P1 over n, P2 over n, etc., and Q1 over n, Q2 over n, etc. Okay? So when we did these embeddings, we embedded the set of partitions of n into this compact space. And what we proved is that the limit points, when we let lambda, the size of lambda go to infinity, the limit points of the values, so on the cycle of length k, of this quantity. So if lambda, so the size of lambda goes to infinity and lambda converges to some value omega, some double sequence like that, then this converges to some chi omega of ck, which is the integral of x to the k minus 1 d mu of omega of x. So mu omega is a certain measure which is associated to the point in the Thoma simplex. And mu omega is just the sum of alpha I delta alpha I, so a sum of Dirac measures, plus beta I delta minus beta I, plus gamma delta 0. Okay. Of course, if k is a 2 or more, this gamma doesn't appear in this formula. It appears by default because it is here just to get a probability measure, the sum. But you never see it in the formulas for the characters, only the alpha and beta count. Okay. Okay, so we proved this last time. Okay, so this shows that if you want to, so in particular, if you take any sequence of characters where the size of the group goes to infinity, all the possible limit points, I mean, there will be a subsequence converging in the Thoma simplex because it is compact, and so we know that a subsequence will converge to that to an expression like that. Okay, and in particular, if we know that this converges, then it will certainly converge to some expression like that. It will converge in the Thoma simplex. Okay, so this is what we proved. So now I'm going to. So just to recall how we got this result, it was just that this is equal to 1 over dimension of lambda times the trace of rho lambda. So rho lambda is a representation associated with lambda, and the trace is taken in this representation space. Gn over n to the k. To the k minus 1. Okay, and here we use that the co-transition measure. I should have stated that this co-transition measure is the distribution or the law, if you want, of Jn, which is so Jn is a certain linear operator. In the space of the representation corresponding to lambda. So if I take as a state the normalized trace, so this operator has a certain probability distribution associated to it, and this probability distribution is the co-transition measure. And this is just by definition in some sense. Because of this definition, you see that the eigenvalues of Jn on this sub-representation is exactly equal to xi, and this is the reason. So this is just saying that is just a restatement of what is in this graph here. Okay. Okay. So now what we understand of the large n limit of these representation of symmetric groups is that we have a kind of law of large numbers for the Jn. Okay. But then so this has allowed us to express and the reason why this is related to that, so this is a cycle of say the cycle 1, 2, k, or any cycle of order k. Okay, and the reason for that is that if you take this to the power k minus 1, then almost all the summands in this expression will be cycles of this length. Okay, if you think of them as when n goes to infinity. When you take k minus 1 elements in the sum here and expand, then almost all of them will be different, and then you will get a cycle. That's the reason why, essentially, you get this law of large numbers here. Okay? So now we are going to see that actually not only we can express, we can find the limit of the CKs, but we can also find the limit of all the for all permutations. So we will see that. So again, assuming that lambda converges to omega in the Thoma simplex, then we will see that the so I recall that this chi omega were the extremal Thoma characters that I defined, but here I can recover them without even knowing that they exist in advance. So these are defined by the fact that their value on the cycle is given by these moments here, and moreover, they are multiplicative. That is, if sigma is written as a product of non-trivial cycles, say C1, C2, or I would call it C1, C2. CR, so some cycles which are disjoint, the unique decomposition of sigma into non-trivial cycles. I don't count fixed points in this decomposition. Then chi of omega of sigma is the product of the chi omega of Ci. Okay. So this means, so in order to prove that, it is enough to prove that I will prove that this quantity, if sigma, what? Excuse me? You have a question? Yes. Right. Okay, the absolute value, or I mean, this quantity. What I will prove is that this quantity is small if sigma 1, sigma 2 are two permutations with disjoint support. By the support of the permutation, I mean the points which are not fixed by the permutation. Okay, we consider them as elements of S infinity. So, okay, so what I do is I fix two permutations, sigma 1 and sigma 2, which have disjoint support. Okay, then this expression has a meaning as soon as lambda is large enough, as the lambda is a partition of some n large enough, because then the n will be larger than contain the support of both sigma 1 and sigma 2. And what I claim is that this quantity will be small. Actually, it will be of order 1 over n. And this will be uniform over all lambda, and all permutation with some fixed size. Okay, so why is it true? Well, this is again the same idea as in this the proof that I made for the using the Jershis-Murphy element. So the idea is the following. So take, well, I make just a first comment. Take a G, a finite group. And take C, a conjugacy class in the group. Okay, so all elements which are conjugate to some element in the group G. Okay, and let me denote C. Okay, again by C the sum. What do you want? I call it C bar if you want, just to distinguish it. It's an element in the group algebra. It's just the sum of all elements in the conjugacy class. Okay. So this element belongs to the center of the group algebra. It's an element in the group algebra which commutes with all elements because it's just it's obvious that it commutes with all elements. So since it is in the center, it commutes with all elements, and so it must be if I look at an irreducible representation, rho, So if rho is an irreducible representation of G, and I look at the image of this element C bar in the representation, it must commute with the image of the representation, which generates the whole algebra. So it must be equal to some constant times the identity, okay? Because it commutes with the image of an irreducible representation by Schur lemma. Okay. Okay. So how do you compute C? Well, if you want to compute C, you just compute the trace on both sides of this equation. So the trace of rho of C bar is equal to C times the dimension of the representation rho. Okay? So this means that this quantity C it is equal to 1 over dimension of rho times the trace of rho of C bar, or if you want, it is equal to it's equal to K rho hat. So this means the character associated with the representation rho, which is normalized, so divided by the dimension, evaluated on the sum of these elements in this conjugacy class. So it is, say, G times the number of elements in the conjugacy class. Okay? So this number here is the size of the conjugacy class multiplied by the value of the normalized character on one element in the conjugacy class. Okay? So we have, and this is the value of this element of this operator, which is a multiple of the identity. Okay? So it is the only eigenvalue of this operator. Okay, so this is true for any finite group. Okay, so let us apply this. So let us look at our two permutations, sigma 1 and sigma 2, which have a disjoint support. Okay, so then what I can say is that so in Sn, the class, so let me call C1 the conjugacy class of sigma 1, and C2 the conjugacy class of sigma 2. Okay, so these two, so the number of elements of C1, well, this is, so sigma 1 has some set of non-fixed points. So let me say that it has k points. The support of sigma 1 consists of k points, and the support of sigma 2 consists of n points. So in order to find an element in the conjugacy class of C1, then I have first to find k points among the n that I have here. So this is a binomial coefficient. And then there is some number, C, say, let me call C of sigma 1, which depends only on the sequence of cycles of sigma 1. It is a combinatorial factor, which tells you in Sk, it is the value, if you want, of this conjugacy class, the size of this conjugacy class in Sk, which is the smallest symmetry group in which it belongs, to which it belongs. And same, of course, is true for No. I'm just looking at the conjugacy class of sigma 1.
Okay, sigma 1 and sigma 2, they don't still have disjoint.
No. They have disjoint support, but when you look at the conjugacy class, you forget about that. The conjugacy class of sigma 1 is something, and it doesn't see that sigma 1 has. This is just a claim about the size of the conjugacy class of sigma 1 and sigma 2. Okay. See, it's a number which depends only on it doesn't depend on n, that's the point. Sorry, I don't know how to call it. Don't call it C if you are disturbed. Pi, okay.
Isn't usually set of lambda?
What?
Isn't usually set of lambda as the size of
Z of lambda is a hull here because you in general you count the fixed points. But here, I don't want to count the fixed points. The fixed points are hidden here, okay? Counting the fixed points. Okay, but this is some number, which the point is that this is a polynomial in N, okay? Which has degree K, okay? And now what happens when I compute so I will compute this, so the trace. So this is.
So you're not writing the size of the conjugacy class of the strata?
No, for the moment, I just expressed the size of the conjugacy classes. Now I'm taking the product of these two elements in the group algebra. And what I claim is that in this product, when n is large enough, most products will be of permutations with disjoint support. That's all. This is a very simple observation. I mean, okay, so what? Here? No. Okay, so this is rho, if you want, rho of this one. Yes, rho. I evaluate these elements in the irreducible representation. Then this is a multiple of the identity. And since it's a product, I just take the product of two multiple of the identity, so it is clear. And now, this is the sum of a W1, W2 of rho of W1, W2 times rho of W1, W2, okay? And now what I claim is that, so I can take the sum, I can make two subsets in this sum. So in this sum, W1 is in the conjugacy class of sigma 1, W2 in the conjugacy class of sigma 2. So, okay, so this sum is equal to the sum where, say, the supports don't intersect plus other terms, okay? And in this, okay, so, okay. And so now, if I take the trace on both sides of this equation and I divide by the dimension, what I get that, but this is equal to, okay, if W1 and W2 have no point in common in their support, certainly the product is conjugate to sigma 1, sigma 2, okay? And there are other terms. And now, how many terms do I have here? Well, if you want to find W2 and W1 and W2 having no point in common in their support, then you choose this. You first choose W1, okay, so you have this number of choice. Then you choose W2, and you have to choose the elements in W2 which do not intersect this one. So this time we have n minus k L pi of C2. Okay, we have to choose the elements in the support of W2 among the n minus k elements which remain. Okay. Sigma 1, sorry. Yes, you're right. Sigma 1 and sigma 2. Okay, and so we have plus other terms, but we see that the other terms, their number is a big O of n k plus L minus 1. So this is certainly something of the order n to the k plus L. And what remains? It remains cases where we have coincidence between the things, but it's clear that this is some big O of a certain polynomial in n to the k plus L minus 1. Okay? And this is equal to, the product, C1, C2, so it's nk pi of sigma 1 and NL pi of sigma 2. Okay? And this is multiplied, of course, multiplied by the multiplied by rho of sigma 1, sigma 2. And here I have to multiply by k hat of sigma 1. Hmm? But the same thing. It's the same thing. You can simplify by n minus k factorial if you want. Now, what I say is that this plus something which is small is equal to this. Okay, but there is some big O of, there is all the terms that you get by when your permutation have some points in common in their support. That I don't want to count them. I just say that their number is big O of n to the k plus L minus 1. Okay, you have one, at least one of the two have to coincide. So the number of choices is smaller.
So you are essentially writing what you have just on its right.
Okay, so essentially this is what is here. You just divide by the n to the k plus L. What? What? So this is the product of the characters, and this is the character of the product here. This? This? Oh, but this is because when you evaluate this is rho of C1 bar, rho of C bar 2. Okay, you evaluate element in the center and they multiply. Okay. So this expression, which is exact factorization, when you look at the level of the permutations in the conjugacy classes, when you have very huge symmetric group, they give you that you have essentially this factorization up to some error term. But you see the error term is like O of 1 over n. Okay? And you see that this is completely uniform over all. I don't use anything about the rho here, about the irreducible representation, only that it is a representation of Sn. Only the size of the representation occurs in this. Okay, there are some factors here, but if you fix the size of the supports of sigma 1 and sigma 2, everything is completely uniform. Okay, so you have some bound which is completely uniform in everything. As soon as the sizes k and l here remain bounded. Okay, so this is just a very simple observation on the symmetric group. The fact that when you multiply very large permutations with very small support, the support in general have a small probability to intersect. That's all. So, and this translates into this asymptotic factorization of characters. Okay. So this means that when we have, this implies in particular this property which is here, that the character, an irreducible character, if it converges to one of the Thoma characters. Okay? So we have first to estimate it, how it converges on the cycles. This is obtained by looking at the Murphy element, just this Murphy element. We see that they are given by the moments of some probability measure. And we have seen that the probability measure, the cotransition measure converges, suitability scales converges to the probability measure associated to the Thoma point. And then when we have done that, then we just have to see that we have this asymptotic factorization, which is a very simple combinatorial thing about permutations. So we see that any limit point that we can find is a Thoma character. Okay, and I mean from that it is not difficult to infer the Thoma theorem actually, because Thoma for Thoma theorem, if you take any of course, any character, any positive type, normalized central positive type function on S infinity you can restrict it to Sn and get a positive type normalized and central function. So every chi will, so if it is defined on S infinity, its restriction to Sn will have some decomposition into irreducible normalized characters, okay, for some probability measure, okay? And now, if you let n go to infinities, and this is a probability measure, so you can embed the lambda into the Thoma simplex. So this gives you a certain probability measure on the Thoma simplex. This probability measure will have some limit subconvergent subsequence which converges to some probability measure because we are in a compact space. And then you will get that any Thoma character will be represented as an integral of the extremal Thoma characters. Okay, so every chi will be obtained as the integral of chi omega on the Thoma simplex, d mu of omega. And now it is not difficult to see that this representation will be unique because if you look at the chi omega of ck, so I can, every point is a Thoma simplex, I can identify it with the probability measure on -1 plus 1. The probability measure, which is the limit of the, if you want, it was the sum of the alpha I, delta alpha I, and so on. So this probability measure, these are its moments. So if you know all the moments of a probability measure, you know the probability measure. So these are continuous functions. So omega, this map, to omega associates the value of the Thoma character on the cycle, is a continuous map on the Thoma simplex, and it separates the points. Okay, so if you know the integral of all these functions, which separate the points, you know the integral. And of course, the chi. Okay, so the chi omega are multiplicative. They form an algebra. Okay, I didn't notice that, but chi. Okay, because when you evaluate them on cycles, they are just the moments of some measure. So when you multiply the moments, you obtain the moments of the measure, which is the multiplicative convolution of the two measures. Okay? So if you want, this is the expectation of x to the k minus 1 for some x, random variable on -1 plus 1. So when you multiply two things like that, you get the expectation of xy to the k minus 1 with two copies, x and y's, independent of the two variables distributed according to omega 1 and omega 2. What?
You take convolution of things which are delta functions, in which sum over alpha is bounded and things like that. Why don't you take a support on things which are outside? For example, those delta functions all have support between -1 and 1.
Yeah?
After you take a convolution, support goes into -2 and 2.
No. Multiplicative convolution.
I mean, can you be more explicit?
Huh? No, it's just a product. If you take product of two numbers between -1 and 1, they remain in between -1 and 1.
You cannot take products of deltas.
Product of the random variables.
Can you define the multiplicative convolution?
You take two random variables, you multiply them independent, and you multiply them. That's all.
Yeah, but if you sample them from delta, Dirac deltas,
Yeah.
the resulting things will be proportional to the product of two distributions. You cannot take the product of two distributions. You can take the product of the distribution times a smooth function.
No. Okay. Let's say you take. Okay.
For example,
Okay. So this is just. Plus.
that product.
Yes, that. You multiply the random variables. You have two random variables which are distributed according to this Bernoulli distribution. You multiply them, and you get a new.
Multiplying the mu. You are multiplying the process.
Yeah.
which is very different from dependent.
Yeah. Okay.
Sorry.
Okay. Anyhow, okay. So what we proved is that. Okay, I didn't. If you want to prove that, you have to put epsilon everywhere and do all the. I mean, I show you enough that you have enough bounds on everything to control the convergence. But basically, what we will end up with will be that we will have product integral decomposition of every character, every positive type function which is central on the infinite symmetry group, into irreducible one, extremal ones. Okay, so the chi omega are extremal ones, and this decomposition is unique. Okay, so this is Thomas theorem. Okay, so. Okay, so it was just a little,
Sorry,
yes?
You define chi as a linear combination of chi lambdas?
Yeah, this is a decomposition. Chi is a character of S infinity. When you restrict it to Sn, you get this decomposition. Okay. Now you let n go to infinity. What I claim is that this decomposition, you can take a subsequent which converges in some sense. So the probability measure will converge to some probability measure on the Thoma simplex. And these things, we know they will converge to some extremal characters. Okay? And then in the limit, we obtain this. Okay? I don't want to go into all the details of all the estimates to prove that really you can do that. I mean, but essentially, I gave you all the things you want. But then
Omega does not depend on the choices you have on pi lambda?
On
the choices you made on pi lambda?
there is no choice here. There is a unique decomposition. This is these elements are the extremal characters. Yeah, but I mean, they are the extremal points in the and it is a simplex. The set of in infinite dimension, it is a simplex. There is a unique decomposition of positive type function into extremal ones, which turn out to be the normalized characters, irreducible characters.
Pi lambdas are numbers.
Yes, positive numbers, and their sum is equal to 1. That's all.
So for any choice you have of these positive numbers, you will always get to the same limit. That's what you say.
There is no choice, I say.
Once you pick.
For each n, there is a sequence of numbers like that, indexed by the partitions. And it is completely determined by k, of course.
There are plenty of keys. Okay.
Oh, there is plenty of n, you mean? Yes, of course. No, chi is fixed. Chi is fixed. And I look at the restriction of k to Sn, which is completely determined by k.
Let's suppose now that you pick another chi.
Yes? Oh, then there will be another sequence. So, yeah, okay.
Sequence. So, I don't know, should you write in the second line, should you write some dependency?
Oh, yes, this measure depends on k, of course. It's a probability measure, which is, in some sense, the limits of this distribution. You have a probability measure on some points which sit inside the simplex, the Thoma simplex, okay? Because these lambdas, I have sent them to the Thoma simplex by using Frobenius coordinates, okay? And so I have some probability measures, and I just need to take the limits of these probability measures, the weak limits, and okay.
So this is somewhat the limit of some point at infinity, but on the Thoma simplex point alpha beta gamma, which makes a random walk down to n where it arrives.
Yes,
but
exactly.
You can take brains into this graph.
Yes, okay. There is yes, you can do that. I mean, this is really what Kerov and Fershik did. So here, I'm just interested in proving the Thoma theorem, but they did a more precise analysis. What they did is they looked at harmonic function on this graph and the limit, in sometimes the Martin boundary of this graph. Okay, so this graph gives you transitions, so you can write down harmonic functions and positive harmonic function and try to describe all the positive harmonic function at infinity. This is given by the Thoma simplex. And really, what Kerov-Fershik did was to look at harmonic function on this graph and compute the Martin boundary of this graph using the representation theory, asymptotic representation theory. Okay. So this is much more precise, and what I'm just claiming here is that you can recover the Thoma theorem just because you know that you have these things here. But of course, you can do better, and you can really compute the Martin boundary of this graph in terms of the Thoma simplex. Okay, this is a theory of Kerhoff and Ferchik, actually. This is how. It exists, yes. Yes. You have a family of probability measures on the Thoma simplex. Because okay, so this is, if you want, this is the sum of p lambda delta lambda, and lambda is some partition, but I send the partition into the Thoma simplex. Okay, so this is some probability measure on the Thoma simplex, and by compactness I can find a convergent subsequence, and what I claim is that in the end you get this. No, because it converges. Because all these functions converge. We know that it converges in the limit. And we know that there is unique decomposition here. So the limit can be only this decomposition. If the decomposition exists, it is unique. Well, that's what I said, because we can find function which separates the points. And then, so if this decomposition exists, it is unique. Okay, and so any subsequence has to converge to this because it is the decomposition. If the point is to find a decomposition to prove that it exists. Once it exists, we know it is unique. So we know that any subsequence which converges has to converge to this limit. There is no other choice. Hmm? What?
You have this convolution.
Yes, yes.
If you have a p lambda of representation 1 and 2, can you get the p of the product straight on, or it's a new calculation?
Oh, it's complicated. At the finite level, it's very complicated. It's taking tensor product of representation of symmetric groups and the Kronecker product, and this is highly non-trivial. I mean, there is no even any non-algorithm, combinatorial algorithm known to do that. It's a very hard problem.
Those were Thoma and not just.
You know, in the limit, it becomes very simple, but at the finite level, it is very complicated. It's a very difficult combinatorial problem. I think there is no really combinatorial answer. The only answer you have is really you compute the characters and you decompose it using the orthogonality, but it's not combinatorial. You have to use signs, and there are cancellations. But in the end, you know we'll get positive integers in the decomposition, but they are very difficult to compute. Only in the limit does it simplify, and you get this formula. Okay, so this was just a remark on the Thoma theorem, but I want to emphasize something which I think is more important, which I will call the factorization concentration principle. Okay, so what I said is that when I have an irreducible character of very large size, the irreducible character factorizes approximately on small permutations. Okay. So now let me look at psi, so a positive type function. On Sn for some big n. Okay, so psi is a sum of p lambda, k hat lambda. Okay, it's a sum over all partitions of n of some. It's a convex combinations of irreducible characters. Positive type, and it is central also, central and normalized. So this means that if you take some elements in the group, this matrix is a positive matrix. So it is a Hermitian positive, non-negative matrix. This is what it means. So this means that psi is if you want, it's a coefficient of the representation, of a unitary representation. A positive type function is a coefficient of unitary representation. And if it is central and normalized, then you can always expand it as a convex combination of the irreducible characters, the normalized characters. Normalized means that it takes value 1 on the identity. Okay, so the p lambda really they form a probability measure on the partitions. More generally, on any finite group, you can define this notion, and you always have this expansion into irreducible normalized characters. Okay, so well, if what I claim is that if p lambda, so the probability measure, is concentrated around some chi lambda 0, say, or the support is, or most of the mass is close to chi lambda 0, then psi will be very close. The value of psi will be very close to the values of chi lambda 0, and in particular, psi will be almost factorized like this. Okay, so this means that psi, if I take two small permutations, okay, with support small with respect to n, this will be like, okay, essentially because all the values of psi will be values of characters which are very close to the values of this character. So this is a vague statement, but what?
Small n is joint or just small?
With disjoint support, yes. This is what I call factorization. Factorization means that if you have a positive type function, if it factorizes asymptotically in this sense, this means that if you take two small permutations of disjoint support, then the value of the product is the product of the values. Okay, this is what I call asymptotic factorization. Okay, and what I claim is that so if I have an irreducible character or something which is very close to being an irreducible character in the sense that the probability measure is concentrated around some lambda, okay, some small set in the Thoma simplex, then I have this asymptotic factorization because we have this, and the values of the chi lambda are all the values of the value of psi are very close to the values of this. Okay. What? Yes. In the if you want, in the topology of the Thoma simplex that I'm looking at.
So lambda is a fixed. Lambda not is a fixed.
There is some. Assume there is some lambda 0 or there is some neighborhood of some lambda 0 which contains almost all the mass of pi lambda. This means that essentially psi minus chi lambda 0 is small.
When n goes to
Yes, I choose a very large n, and I assume that I have my psi is concentrated around this chi 0. This means that psi is essentially a small perturbation of chi lambda 0. Okay, then of course I have this, because I have this for chi lambda 0, and if I have a small perturbation, this is true again. Okay.
Why do you need a single lambda not?
Oh, any lambda 0 which is close enough to any lambda prime which is close enough to lambda 0 will work. It's the same.
If you take a measure of all the lambda not which have a size smaller than some fixed n not. Valid or not?
All the lambda.
You take all the tableau, a measure of all the tableau with a finite size. N not.
No, but lambda 0 has size n. No.
But then what does it mean when n goes to?
No. You see, this is a lambda. It belongs to the Thoma simplex. Okay. So in this sense, in the Thoma simplex, I look at a small neighborhood in the Thoma simplex of lambda 0.
So it's not when you say it's small, it's not the statement that it's O 1 over n.
This difference? Well, this depends on the value of this difference. There is no reason to assume it is big O of 1 over n. I just say it is small.
It's small, it's of the same order than the difference between the psi and psi lambda naught or something like that.
Yes, I mean, we know that this is almost factorized, okay, up to big O of 1 over n. So what I say is that psi also will also be factorized up to some error, but the error, of course, depends on the errors that you have here. That's all. That's nothing more. Okay. I mean, it's nothing deep what I'm saying here. It's just a constatation that if you have a function which is very close to a function which is almost factorized, then the function itself is almost factorized. I mean, if you evaluate this on a set of, say, the set of all permutations which have a fixed size of the support is not larger than some k, then you certainly will have this property. This is trivial, what I'm saying. It's just nothing deep. But what is less trivial is there is a converse statement, of course. The converse statement is much more interesting.
But I'm sure that it's not deep, because normally concentration, say that it was a random variable. Concentration means that P lambda are under 1 over square root of n, instead of being over 1 over n. So all the P lambdas are very small. It's just that the key lambdas are very similar.
Yeah, what I say is that, of course, you could have the P lambda could be very small, but spread on a very large set of lambda, but the lambdas will be very close in the Thoma simplex. If n is very large, this can happen.
So the relation over that doesn't apply immediately, only applies to a fraction of 1 over square root of n of the n.
Because what I claim is that this will be small. If this difference is small, then you can replace here this by psi, and this by the product of the psi, and the error is small. Yes?
Is it possible to make here some kind of a uniform bound, telling how close you should be and how small these things will be?
No, I mean, this is trivial. I mean, suppose that this is smaller than epsilon over all sigma, then psi of sigma 1, sigma 2 minus chi lambda naught will be smaller than epsilon. And then psi of sigma 1, psi of sigma 2 minus chi lambda 0 of sigma 1, chi lambda 0 of sigma 2 will be smaller than epsilon. Okay? And then the difference between that and that will be smaller than 1 over n. So the sum will be smaller than 2. The difference will be, so this difference here will be smaller than 1 over n plus 2 epsilon. That's all. It's a trivial, I mean.
But how
I
close?
don't want to make any hypothesis here that this goes like 1 over n or anything. I just say it is small. It is smaller than some epsilon. If this is smaller than some epsilon over all the small permutations, then certainly I will have this triangular inequality. I mean, this is completely trivial. There is no...
So you're not claiming how fast it goes to 0. Is that
No. I'm just saying it is small in some sense, in the sense that it is smaller than epsilon. Okay. This epsilon may not be that small. It may be 1 over log n, or I don't know, something. It should not be too large. But what I claim is that you have just a triangular inequality, which tells you that this here will be small of this order epsilon plus maybe something which is 1 over n. That's all. Okay. But of course, but as I said, this is just triangular inequality. This is a trivial statement. What is more interesting is that there is a converse statement. The converse statement is that if we have such an asymptotic factorization, then the psi is concentrated around some chi lambda. Okay. And again, this is not so. This is a little bit deeper than what I'm saying here, but it's not much deeper. It is again the same idea that in my product of large conjugacy classes, I have something which happens with probability 1. That's all. So so let me try to give a statement. Where did I put my statement? Okay, so assume that okay, no. Let me take some L, large number L, and take epsilon, or say delta, positive. And now, what I claim is that there exists epsilon such that if psi of sigma 1, sigma 2 minus psi of sigma 1, psi of sigma 2 is smaller than epsilon for, so again, the two permutations have to be disjoint, and their lengths have to be smaller than L. Okay, so I fix a certain set of lengths of permutations, length of the support, and I assume that I have I have asymptotic factorization in this sense that if these are small enough for over all these permutations, and take or say there is x epsilon and there is x n, such that if I have some positive type function on Sn, so psi is positive on Sn, then, so in particular, psi can be written as a sum of characters. So what I claim is that this probability measure is concentrated. So the probability so here the random variable is lambda, which is here, which I take with the value p lambda, with the probability measure p lambda. This means that in my decomposition, p lambda will be concentrated around some values, and the values are just the values of psi. Yes, this is what I mean by big O of 1 over n. When oh yeah, no, sorry. So, no, there not no. Okay, okay. So the statement, sorry, the statement is that. Okay.
So there is one lambda such that.
Yeah. There is no. Lambda here is random. I'm taking the probability with respect to this measure, p lambda. So lambda, what I say is that all the lambda, or the support of the probability measure, is such that the characters in the support of this measure are very close to the values which are here. This is what I claim.
For each sigma.
For each sigma.
Yeah, yes, for all sigma with say L or maybe L over 2 or something like that. Okay.
What is that?
N, because psi is on Sn.
Yeah, but then the estimates should degrade when L grows.
So there is some big O of 1 over n which depends on epsilon and L.
Epsilon and L. Okay,
Yes.
So it's not a species, not L over n.
Or you can make it explicit. I will show you. It's very simple to make it explicit, but I don't want to do it because, I mean, just a computation is not very interesting here. I mean, if you really want to make an explicit estimate, you can do it. It's very simple. It's just Biane-Chebyshev, essentially. What I prove is that, this is the value of this. Okay, when I evaluate this on sigma, it is a random variable with respect to lambda, and I prove that just that the variance goes to 0.
But you claim that this measure on lambdas concentrate around something, or you don't claim that?
In some sense, I claim that they concentrate because the probability, you see this, what I claim is that the coordinates, if you want, on lambda, that when you evaluate on some permutations, they concentrate on this value, okay? They are all very close to this value in the support. Most of the mass is, of the measure is on characters which take value close to this psi.
But is it possible to rewrite it in some usual topology on lambdas, like the first rows, the first columns, whatever?
Well, it is just, if you want, it is just the topology induced by the evaluation of characters. That's all.
I'm asking, is it possible to rewrite it in more usual topology, like the first rows of lambda, or first columns?
Well, if you want, if you embed Thoma, this in the Thoma simplex, this is essentially a product of the moments. This is one way of looking at it.
May I say, Philippe, I think that it is really crucial the fact that there is a capital L which is born, because it makes no sense.
Capital L.
L.
Yes, of course. L has to be bounded. It can be large, but it is bounded. You take it at the beginning. You take L, say all permutation with size smaller than 100. You take some delta small, and then I say that if I assume this for all my permutation with a sufficiently good estimate, then I have this concentration which occurs.
So let's say when you take the sum of a p lambda, p hat lambda, p hat they are vectors of dimension capital N.
There are
They
vector.
are vectors. They are there is an argument which is a conjugacy class.
Yeah.
And in capital N, there is no possible concentration because they are just all orthogonal. That's in the projection over those columns in which L is bounded, in which they start to be all similar if lambda are similar. But the tail is completely, the tail is making the orthogonality.
Maybe, I don't know. I'm not sure I understand your argument, but I mean, this is actually, you will see this is very simple. There is it's not a big trick here. It's very simple. It's always the same thing, that when you multiply conjugacy classes, there is one overwhelming case, and the other cases are very small. That's all. So what is the idea? I just give you the idea. I will not just... So let me write. So this is the sum of p lambda. Okay? But this is not very far from okay? But this is also not very far from the sum of p lambda because this is because of the factorization property of psi. Okay, the difference between these two things is smaller than epsilon. That's my hypothesis on psi. And now the difference between these two things is small. It's something like that. Okay, and now it's finished because you see, you look at the random variable chi lambda of sigma. You see that for different sigmas, you see that all their covariance go to 0. So they must be concentrated, that's all.
So this miracle that vectors which are originally orthogonal
Yeah.
under this projection becomes
not collinear because they are collinear on a small subspace. I mean, because of this.
Small subspace.
Yeah.
Projecting to small subspace of bounded L, orthogonal vectors become collinear.
Yeah. No, this means they are not collinear. This means just that essentially psi is concentrated around one of the characters. That's all. That's what I mean. If psi is equal to chi lambda, this is true. And this is what happens in practice. This is there is nothing that orthogonality or so on. You just.
In practice, P lambdas, they are all under 1 over square root of n or something.
No. They can be what you like. I mean.
But they are surely.
They have to be. They just have to be concentrated. That's the statement. They have to be concentrated. This is psi of sigma 1, psi of sigma 2. Okay, I'm saying this is true, but it's my hypothesis, which is here. I have to make this hypothesis. That psi I say that psi factorizes. If psi factorizes, this imposes all the these random variable to be. Okay. Okay, you're right. If I write some notes, I would put it in the better order. But
this probability here, cannot repeat this? This probability that you wrote in the last line.
it is this probability. It's a probability on lambda. I said lambda is taken at random here, according to this probability. And what I say is that this probability, which gives you the decomposition of psi, is very much concentrated around some character. And there is nothing deep. I mean, it is just. Yeah.
That means you assume that the inequality on psi sigma 1 will be true for all sigma 1 and sigma 2.
Yes, I assume that this is true when you have disjoint support and the length of the support is small enough.
Where do you use this? Where do you use that you need a bound on the support?
Because I use it here. Here, this is true, but this is not uniform over all permutations. It's only permutations which are small with respect to n or fixed. Okay, I said this factorization holds, but it holds only for small permutation. I cannot. It will not be true for a very large permutation of the size with support of the size n over 2 or something like that. In general, it will not be true.
Actually, when you try to see two cycles match on each other, there is some, that's the paradox, that's L squared over N. If two cycles have a size L,
Yes.
they hit with probability L squared over N. So the first correction is in L squared over N, in order to
Yeah.
be safe.
But here, L is fixed. Doesn't grow. Okay? It doesn't grow, and of course, the conclusion is only about these permutations. You cannot say anything about the value of psi compared to chi lambda on larger permutations, of course. You cannot say anything. Or maybe L over 2 because sometimes I have to take products, so it will be true with L over 2. I didn't check whether you can assume just L. But. Yes?
So, your assumption is that psi is
Yes, I say if psi is an irreducible character, then asymptotically it is multiplicative. And I say conversely, if psi is asymptotically multiplicative, then it is very close to be, in this sense, it is close to being an irreducible character. So this is what I mean, the concentration factorization. Concentration is equivalent to factorization in this sense, weak sense. Psi, no, what I say is that psi, it's a convex combination of extremal characters. And what I say is that this p lambda is very much concentrated. The probability that the value of the character is away from this is small.
if your psi hat is not an extremal character, it's a character.
of?
Caractère of S,
No. There is no character of S infinity here. Everything holds for finite characters. It's not a statement about infinite characters. It's just a statement about finite symmetric groups with large size.
Yeah, but hidden behind is something like we want
Yes.
to be near to
No, I mean, this is the finite statement which corresponds to the fact that for extremal characters, on the infinite symmetric group, we have the exact factorization. Okay, so we have this exact factorization for infinite characters, and this comes from the fact that S infinity contains this as a subgroup. And what I claim is that there is a finite approximation to this equality, which is this approximate factorization, which tells you that if your character is irreducible, then it is approximately factorized. And conversely, if the character is approximately factorized, then it is almost an irreducible character in this sense, that it is closed on a permutation of fixed size. It will be close to an irreducible character, some irreducible character. Or its measure it will be not very much spread over the Thoma simplex. Okay, so this is what I call the approximate factorization concentration principle. Okay, and this you see, basically it uses almost nothing of the symmetric group, very small thing of the symmetric group. That's the fact that when you multiply two permutations with small support, very large permutations in a very large group, you take a small two small conjugacy classes. When you multiply them, almost all the time you get the same result in the product. That's the idea behind this factorization concentration principle. And we will see that there will be a similar principle, but much more subtle in the case where we let when we will do the other scaling by square root of n. There will be something else, but it will use much more of the geometry of the symmetry group. We will go it will use a Cayley graph and things like that. Here we are just essentially using what Vadim called the Hamming distance. So it is a very simple, very crude asymptotic estimate using the Hamming distance. But when we will make the other scaling, we will use really the Cayley graph of the symmetry group that I introduced in the other lecture, and then it will be much more involved than here. You see, okay, so you have to get to understand exactly what is the meaning, but I mean the mathematics, the combinatories behind this is very almost trivial. I mean, just counting, elementary counting on subsets of 1n. Very simple. No. I don't have time to go into a discussion. So what time is it now? Okay. I forgot to make a break. You want to make? Does someone want to make a break or? It's too late. Sorry, I was into my. Okay. So okay, I mentioned this. Okay, here this is quite simple. I mean, you really. I mean, you see that. We are using very crude properties of symmetric groups, and we will see this principle come again in a more refined way later when we go. Okay, but I want to finish with this, say, law of large numbers of the representation of symmetric groups. So for this, so I will go back to the Thoma characters. And we will see that they have really a nice significance, even when we can even decompose them on their restriction to the symmetric group. And it's a very nice computation, so I will explain it. So for this, we'll need to use the Schur-Weil duality. Okay, so it's a very important thing about representation of symmetric groups. I never mentioned it and never used it before this, but now I'm introducing it. And actually, you can even base your theory of representation of symmetric groups on the study of this Schurwald duality. If you look, for example, in the book of MacDonald, this is how it is done. So what is the Schurwald duality? Well, it is just the, I will explain. So we have this group Sn. So we saw that it was very important in order to understand Sn to understand the action of Sn on, say, the L2 space of Sn, the space of function. And there were two actions on the right and on the left. Okay, so you multiply a permutation on the left or on the right, and this gives you two actions, and the two actions commute on the space of function. And we saw that decomposing this action, we actually got all the irreducible representations. Actually, this is true for any finite group, of course. It is a general theory. Okay, but now what does it mean? Suppose you have a permutation. Like that, a permutation of 7. So you have one of the, and suppose you want to apply, say, the transposition 3-4 to this permutation. So you can either act on the left or on the right. So if you act, say, one of them consists in exchanging the values 7 and 1, which are on the position 3 and 4. Okay, so the permutation you obtain will be 2, 3, 1, 7, 4, 6, 5. And the other will just, you look at where 3 and 4 are, and you exchange their positions. Okay, so that's the description of the right and the left action. And I cannot tell you which is one is the right and which one is the left, if you are able to do that in your head, okay, but okay. So one of them is like that, and the other one is like that. Okay, and now it's you see that, well, you can, of course, exchange the positions of the values, but it's easy to extend this action to an action on words, actually. Suppose instead of looking at permutation which are special words, suppose I have some words, say alpha, beta, gamma, etc., in some alphabet, alpha, beta, gamma, and I looked at words in my alphabet, but this time I may have repetitions, okay? Then what I can do this time, I can move the letters, permute them. So I have an action certainly of the symmetric group by permuting the letters of the word. And there is and if I have some group which acts on these letters, I can on each place replace each letter by some other letter. Say I have the group of permutations of the letter which acts. Okay, and I can even linearize this action. And what I can do is I can take the following thing. I can take some space. Suppose that my alphabet has D letters, and I want to look at words of length n. Okay. Then you see on this space there is an action of the symmetric group Sn. So just a permutation of in a tensor product, you can permute the elements of the tensor product. And the group GLD of C acts on all the components of the tensor product. So if I have a matrix G in GLD of C, the matrix just acts by like that. And it is obvious that the two actions commute. Okay, sigma G commutes. Okay, so you may think of this as a generalization of the two actions of Sn by right and left, okay? because one of them acts by just permuting the entries, and the other permutes or is an action of a linear group on the vectors. Okay, so it's a kind of generalization. And now there is a theorem that I can decompose this action, this space, into irreducible components. So here I have two groups which act, so, and they commute. So the product group acts, and now I can decompose according to the action of this product group, Sn times GLD of C, and I will have a sum of lambda, partition of n, of say V lambda tensor W lambda. So V lambda will be just so V lambda here will be just a space carrying the representation of the symmetry group. And here, okay, so this will be an irreducible representation of the GLD of C. So we know that these are indexed by sequences of integers with length d. So here I have to restrict to the partitions which have at most d rows. Okay, and we have this decomposition here. Okay. So now I can use this action of the symmetry group to generate, in a natural way, some characters, some positive type function. So let psi be a non-negative matrix of trace 1. Okay? And let me define the following function. Phi of sigma will be the trace of sigma times psi tensor n. Okay?
That's the thing you mean with respect to the determinants of minus, not with respect to
With respect to?
determinants of minus and positive.
It's a positive matrix. No, Hermitian positive, in the sense of Hermitian positive matrix. So it is self-adjoint and it has positive or non-negative eigenvalues. And the trace has to be equal to 1. No, not necessarily. Not necessarily. Some eigenvalues may be 0. It's not necessary to have strictly positive. So this is in the space CD tensor n here. So this is an element, psi tensor n is an element, it's a matrix, tensor n, so it's an element acting on this space. It's a matrix, it's an operator acting on this space. Sigma also acts on this space. And they commute. Sigma and psi to the n commute, clearly, because psi is invariant by permutation. So this function will be positive, non-negative. So it's a positive type function. It is central because, why is it central? Because psi and sigma commute. So if you evaluate phi of sigma 1, sigma 2, this is phi of sigma 2, sigma 1. Okay? Because they both commute with psi. So you can permute inside the trace. Okay? So certainly it has some decomposition into irreducible components. Okay? And so we will compute that. And okay, so let me compute phi of sigma. So if you want to compute phi of sigma, take a basis in which psi is diagonal, and let me call x1, xt the eigenvalues of this psi. Okay? So take x1, xd, the eigenvalues of psi, and look at and take this as a trace, evaluate the trace in the basis formed by all these vectors.
Excuse me?
And yes?
I'm lost on what is the claim. I mean, you claim that there is this equality of the...
Yes. Well, for the moment, I'm not using that.
Okay.
I'm just doing this computation, and I will use that later.
But you took a psi.
Yes. I say if I have a Hermitian positive matrix, then I can associate to it a positive type function on the symmetry group.
So psi.
By this formula. It is a coefficient of the representation, if you want. So it is positive type, because psi is positive.
And now you're proving this?
No, I am computing phi. I compute phi. I evaluate it on sigma, on a permutation.
Okay, so far you're not proving anything.
I'm computing sigma phi. What I claim, this is a positive type function, and I will compute it, and you will see the result is nice.
So the theorem will be after. Okay.
I will compute this, and then I will use this result to provide the expansion into characters. Okay? But now the claim is that, well, you use this, so you want to use, if you have a vector ei1, ein, and you apply sigma to it, this is ei sigma 1, ei sigma n, okay? And you want to take the inner product with ei1, ein, okay? And you want to make the sum over this, and you want to make the sum over this and multiply by the eigenvalues of psi, okay? Because the E is the eigenvectors according to psi. So when I apply psi, I multiply such a vector by some factor, which is here. And then I do that, and then okay. When I compute the trace, of course, I have to take all these basis vector, and I want to compute all these inner product and take the sum, because this is a trace, okay? That's all. And now you see that, yeah, and now when is this non-zero, then I need to have I sigma 1 equals I1, I sigma 2 equals I2, etc. So this means that I have a sequence, I have a word in the indices here, I1, In, and I want this word actually to be constant under the action of the permutation. This means that for each orbit of the permutation, so for each cycle of sigma, I will have a constant, some constant vector ei. The I will be the same in each cycle of the permutation. If not, then the contribution is 0. Okay? For each cycle of the permutation sigma, you see that the index has to be constant on the action of the permutation. So suppose I take a word like E1 tensor E2 tensor E1 tensor E3. Okay. And then only the permutation which permutes, which is the identity or which permutes 1 and 3 will leave me this vector invariant. Okay, that's what I'm claiming. So I need that on the cycles of a permutation, the index has to be constant. Okay. So I have a word in the indices of the vectors. This word gives me a partition of 1n here, and this partition has to be finer than the partition induced by the cycles of sigma. I claim that on each cycle of sigma, I need to have a constant, the vector has to be constant on each cycle of sigma. Okay? So, and... because here I have to multiply this by xi1, xin, because psi, these are eigenvectors of psi with eigenvalue xi1, xin. Okay. So now I have to make the sum, and if you do the computation, you see that this is p sigma of x. So if you take the sum of all these eigenvectors, of all these bases of eigenvectors, you find that the value of this trace is equal to p sigma of x, which is, so what does this mean? Sigma, I take the partition of sigma into cycles, non-trivial cycles. So say sigma is, say, 2k2, 3k3, etc. So there are k2 cycles of length 2, k3 cycles of length 3, and so on. Okay, there is some sequence. And this is the product of pi of x to the ki. And pi of x are just, pi of x is a sum of xj to the I. Just the power sum function. Okay. What? No, well, no, because P1 is equal to 1 here. The sum of the xi is equal to 1. This is what I assume here. This is some assumption I made, so I don't have to. I don't need to count the P1 here. Only the P2, P3, etc. Okay. Yeah, okay. So it's not. It's just that I want to normalize my thing, so that I want to be able to change the n of the Sn without too much problem, and so it's.
So can you repeat why you get p sigma of x?
Well, you have to do this computation here. You have to see that on each cycle, so on each cycle I will have to sum. So if I have a cycle, then I will get some xi to the length of the cycle. Okay? Because the I will be constant on the cycle, so I will have a factor like that.
Why do you have this factor?
Because in some, for example, here you have this and this, so you will have an x1 here and x1. Okay, so you will get an x1 squared if you have a cycle of length 2.
You're still talking about the inner product you have.
Yes, in this inner product. So this inner product, it will be 1, but I have to multiply it by the value of the eigenvalues of this operator, which is here.
Why do you have to do that? Why do you have to multiply?
Because when I compute the trace, I first apply this, and all these are eigenvectors. So I have to multiply by some x, some multiple of some product of x. Xi, yes. There is some monomial in xi coming from this factor. Then I compute this inner product. And this inner product can be non-zero only if the indices are constant on each cycle. So you get products. You see here you will get a x1 squared, for example, and only if the permutation exchanges 1 and 3 or leaves them constant. Okay, it's good to do the computation yourself. It's a nice computation to do and to understand. It's not difficult, but you have to really do it just to make sure. So you understand. So we have this, and now there is this Schur-Weil duality, which tells us that this. So P sigma, so safe. This it will be the sum over lambda of k hat lambda of sigma, and here I need to evaluate rho lambda on say some psi. Okay, and this. Okay, I multiply by dimension of lambda. So this is a normalized, sorry, I could put it here. I apply the equality which is here. Okay, so when I compute this character, I can reduce into irreducible components. And here, I have some representation. And here, what is not obvious, but is true, is that the representation gives you it is a sure function that you get here.
And why is not? We were having power sums a second ago.
Yes, but here it's of x What I say is that the power sum function, if you can think of this as a function of x or a function of sigma. As a function of x, this is the expansion into sure functions. As a function of sigma, it is the expansion into characters. And these are the power sum functions. What? Yeah. Yeah, that's why I put here. So if you really want to find the decomposition, you have to multiply this by this to get and you have to divide everything by the dimension of that. No, sorry, no. No, sorry. If you take the identity, it's 1. Okay, no, it's okay.
So the x are positive under our assumption.
Yeah, non-negative. Some of them might be 0, but okay.
But this is just algebraically.
Yeah, yes, it's true algebraically, of course. But here I'm using it with positive entries. Now you have to recognize something, that what is P sigma of x? So phi of sigma, so this is P sigma of x. And this is a Thoma character as a function okay, because these are the sum of the xi to the if you evaluate it, it is multiplicative on the cycles, and if you evaluate it on a cycle of length k, this is this. So it corresponds to the sequence. Say if we order the x by decreasing. So it is a sequence in the Thoma simplex. It's an element of the Thoma simplex. And we see that this is, so we see that actually when we restrict the Thoma character on S infinity to Sn, we obtain this decomposition. We have an explicit decomposition, which is here. And of course, these characters are multiplicative. Okay? So this means that this decomposition will concentrate around some lambda, as I said before, because we have multiplicativity. It's not only approximate multiplicativity, here it's exact multiplicativity. Okay. But now, of course, we don't have all the Thoma. So you see, we have an interpretation of the Thoma characters when we restrict to the symmetry group of finite type as coming from this Schrovile duality, from the action on this product of spaces. Okay? But now what happens if we have negative here? Well, if you multiply, if you, instead of taking this representation that I mentioned, you multiply it by the signature representation, if you consider phi times epsilon, epsilon is the signature of a permutation, then what you obtain is a Thoma character with a -1 to the k here, corresponding to the sequence minus x1, minus x2, minus xd. So a sequence in the Thoma simplex consisting of negative numbers, negative real numbers. Okay? And now, well, okay, what happens, how can you do to have the two together? Well, I don't know. I don't have time to. Okay. Okay. I just explained in one minute. So what you do, instead of taking c to the d, you take a vector v, which is graded. You put a graduation, v plus and v minus. On v plus, you let so you take the tensor product. On the copies of v plus, you let the symmetric group act. And on the copies of v minus, you let the symmetric group act with this. The signature. Doesn't work? There is some supersymmetric action on this. Yeah. Yeah. Yes. Okay. Okay. Well, if you permute you have EI and FI. If you permute the I, you can permute Z. If you permute the F, you can add the signature.
What, I'm sorry, I'm confused. What is exactly phi?
CD. You are not convinced? Okay, maybe I'm not so sure about that. So okay, there is some way of acting on this space. I'm not so sure. It's just tensoring by the. Okay. Anyhow, there is a way to construct it to construct an action of the symmetry group on some graded space, which maybe is not as simple as I thought. You may be right. I have to check that. What?
Plus real or complex?
No, these are just CD and CD prime. Oh, no, okay. You just take two subspaces. You have just two subspaces. That's all. You have two orthogonal subspaces. That's. Yes, of course. Yes. Now in the dual, you have something more complicated because you don't have Schur function, you have supersymmetric Schur functions, which depend on two sets of variables. So it's not a duality between Sn and GLN, it's a generalization of the Schur-Weyl duality where you have the action is not, on the other one, it's not GLD, some super thing. Anyhow, it is possible to express these using here a super Schur function, supersymmetric Schur function. Yeah, something like that. Yes. Okay, I don't want to go into this. I mean, just to say that there is also a construction here, and you get here supersymmetric Schur function, which gives you the decomposition of the more general Thoma characters with only finite number of entries, but.
By supersymmetric Schur function, you mean in two sets of variables?
Yeah.
Can you
which correspond to this and this.
Two sets of variables
Yeah. Okay, so anyhow, I will not come back. I mean, it was just to show you that the Thoma characters occur in a very natural way when you have the Schur-Weyl duality. The gamma. No, you have to go to the limit. You have to take an infinite dimensional limit. I think, or maybe if you could. Um,
It has to do with the exit at R0.
hmm?
It has to do with the exit at R0.
No, because the sum has to be equal to 1 if you want it to be normalized. No, it's more subtle.
Trace of psi was 1, right?
Hmm?
But now it's a supertrace.
Yes? But, well,
I don't know if this is a way of saying that, but S lambda of xy can be seen as by stacking transfer matrices of one type and another type, discrete one. And the gamma will be a time evolution of a continuous array.
it's not clear for me, but I don't know. Maybe it's...
So what you're saying is that gamma just take x1 equals 1 over n, x2 equals 1 over n.
Yes. It's a limit, but you have to take a limit. It's not... you cannot realize it... You have to take a limit in infinite dimensions, certainly. Okay.
So your condition then to fix the trace, you want
This was somehow...
artificial anyway.
It's not artificial because I want that phi of the identity is equal to 1. Because if it's not true, well, okay, these are normalized positive type function. I mean, I could not normalize them, but I mean, if I want to have a simplex, I need to normalize them. If not, I have a cone, and okay. So it's important to make such a normalization at some point. You want to have a compact space and a set of extreme points and to have integral representations. That's why you make this normalization. In general. Okay, so I don't know what time it is now. Okay, I have just a few minutes left. Okay, so I will explain in 2 minutes what is coming next. So what we have seen is that the Schur-Weil duality it allows us to go from representation of Sn to representation of GLD. Okay, so there is a connection between representation of Sn and representation of GLD, which goes through the Schur-Weil duality. Okay, so representations. Now, what I claim is that there is the representation theory of GLD, so I have not talked about the representation theory of GLD, and I will not say very much about it, but it can be seen, it has a so-called semi-classical limit. And this semi-classical limit, in some sense, is a theory of random matrices, or some part of the theory of random matrices. I will explain that.
Semi is not really a 1/2.
What? Semi-classical, okay. Yeah, you're right. You're right, it's not half classical. Semi-classical limit, so that means when the Heisenberg, the Planck constant, sorry, when the Planck constant goes to 0, and because this is a non-commutative theory, and this is commutative, how you say, but matrices don't commute, so that's true. But there is some commutativity in the sense that the entries of a random matrix, they are generally commutative random variables. And here, I will look at the representation theory of GLD as providing me matrices whose entries are themselves matrices and don't commute. And this will be... okay, and now random matrices, when the size goes to infinity, we know it's a very interesting story, and there are lots of things about random matrices. And here I will be interested in one of the aspects of this random matrix theory, which is the theory of free probability. So free probability, maybe most of you don't know what it is or know very little about what it is, so even if there are some experts in the room. So free probability, so it's a theory of random variables which don't commute, non-commutative probability theory, and which allows you, so for example, to say that if you have two matrices X and Y of very large size, you know the spectra, and then you can predict what will be the spectrum of X plus Y, for example. This is the kind of thing that you can do using this free probability theory. So there is some relation between representation, which is quite far-fetched, because we have to go through all these things here. So but we will see that there is actually a very direct connection here. And okay, maybe I would say here we will have some random matrices with non-commuting entries. And what will correspond to these random matrices with non-commuting entries? So here we have random matrices, classical random matrices. And what will correspond to these random matrices will be exactly we will see that the Jershis-Murphy element will be what we need when we go from this to this, which is quite nice, that we will have a very natural way of introducing the Jershis-Murphy element from the point of view of representation theory of GLD and its connection with random matrix theory. And here there will be a close connection. Why? Because this free probability theory, it's a theory, it's both operator algebra theory, but it contains also a lot of combinatorics. And it is based on a certain family of combinatorial objects. And this family of combinatorial objects are the non-crossing partitions. Okay, so the non-crossing partitions are really fundamental in this theory to make computations. And it turns out that non-crossing partitions are related really to the symmetric group, to the Cayley graph. Okay, I showed you in the second lecture that the Cayley graph of the symmetric group contains a copy of the non-crossing partitions. Okay, so really, the reason why there is such connections is, of course, we can go through this, but it seems that we lose a lot each time we go from one to the other. But actually, we are never quite far from the beginning. So the next lectures will be okay. In the next lecture, I will explain the basic about free probability theory and its connection with random matrices. Okay, and then after we will see why it is important in order to understand the limit of the symmetric group when the size of when the scaling is given by 1 over square root of n. Okay, so we will scale a diagram by 1 over square root of n in each direction, and we'll see that free probability will appear from that scaling. Okay, so it will be very different from the Thoma theory, which was the law of large numbers. In some sense, this is the second order asymptotic. All the Thoma characters in this regime will go to 0. They will converge to the character of the regular representation of S infinity. But they will go to 0 at a certain speed, and we will need to measure this speed, the speed of convergence to 0. Yes?
To make sure I get big N is small d, right?
Yes, it's D. Yes, it's GLD, random matrices. Yes, you're right.
And your scaling, is it from the symmetric group, small n, or small d?
Here is Sn, yes, small n, yes. Small n. Yeah, okay. I'm not always consistent in my notation, sorry. So this is a Sn which is here.
That's fine.
So here I have Young diagrams, which I will rescale according to 1 over square root of n. And we will see that free probability arises in this regime. Josh's Murphy, they come from SN. I introduced them just using SN. But they arise also, since they are in the commutant of SN, if I look in the Schurweil representation, they belong also to the center of GLD. Because it is something which commutes with SN, and so it will commute also with GLD, and it will so it will be also in the center, some element in the center of GLD. If we interpret it as an element in the center of GLD, it is something, and it's something else here. And when we do that, we will see that we will have this interpretation. Okay, thank you very much.